is Rama Alama. I am 13 years old and today we're going to talk about the immune system. Now, from a long time ago, we need to start off simple. Let's say 18.5 million years ago, before the dinos and everything. In this life world, we have bacteria, fungi and plants. There was no walking or breathing animals in this era. The first living beings were mostly cellular beings, means they coagulated. Here, these beings lived, thrived, and cooperate. Until then, one day, a cell ate another. Normally in the past, to get energy you have to eat something. And the only thing these cells could eat is themselves. So they ate and ate each other until a difference occurred. One cell ate another but didn't swallow it. It was inside of it. The cell inside is called the mitochondria right now. Then this cell started to multiply. Instead of the copy attacking the original, they decided to cooperate. Slowly by surely, they made beings from the oceans to the land to the air. Now we're in page 2. What does your immune system defend? Now, we're talking about your body, basically. From where we left off of the first living things on Earth. Now, we're going to talk about what are they defending. What is your immune system defending mostly? Now, you as a whole is a human being, full of thousands or 4 trillion cells. So much to protect, I guess. Now here in this second page, it's mostly talking about how these cells react. Now we have 4 billion of them in your body. But that's the most of it. Now, what cells can they be? Basically for the whole of page 2, we talk about what these cells are. These cells help you to eat, breathe, think, and cooperate together to do many things that not even one cell can. For example, you can't lift a book by one cell. The book will be 1,000 times larger than a cell. Cells are micrometers smaller than the book. But together they make a hand, and the hand can surely lift the book. Now, what are these? What are cells? Cells are creatures or living things that make another living thing. Like they make organs to tissues to body parts. Now, we have different classes of cells. We have blood cells, muscle cells, neurons, fat cells, epithelial cells, and immune cells. But for now, we're just talking about the immune cells. Now, for the immune cells, each cell has its DNA and makes its different types of proteins. For example, you can see here we have antibodies, glutamine, and also Epsis. Let's continue more. So, after we learn they create proteins, the proteins help the cell do something. Proteins are the talking of life, the way of life works. See, cells are made out of proteins that help them move, react. A protein alone is smaller than a cell. So small you cannot even see it. Even using a microscope, you cannot see a cell. It's too small. You cannot see a protein. One protein does nothing, but together they make something that moves, talks, breathes, just the same. We call this emergence. Emergence is when smaller things merge to be one big thing. Then that one big thing makes a giant thing. And that giant thing can do things that the smaller things can't. Now we're talking about immune cells. Now we have macrophages, dendritic cells, neutrophils, natural killer cells, the complement system, and also natural killer cells, T cells, B cells, and finally eosinophils, basophils, and mast cells, and also antibodies. Now all of these are the main parts of the immune system. There's different types, sure, but we're talking about now the main parts. Each of them has verified jobs. For example, antibodies cling to bacteria, stopping them from moving and attacking. For example, here I demonstrate a bacterial infection. As you can see here, it starts off by the immune system fighting, then a dendritic cell finding the right T cell. The T cell multiplies, then the first group of T cells have their innate, while the second one activates B cells. The B cells multiply, make antibodies, and the antibodies, as long with the macrophage, clear out the infection. And then at the end, we can see most T cells die. Because while your immune system is powerful, it also uses your very resources you need to keep living. So, to not waste any more proteins or resources making these T cells, some T cells remain to make memory T cells. Those ones are the few that remember forever in your body. Most of them die and some live. Same to B cells. While most of them die, some will live forever. Now we're going to talk about an infection, catastrophic damage. Now I want you to meet your enemies in the body. We're going to talk about bacteria, and we're going to also mention a few of our players. For example, we're going to meet the most popular video ever, Naegara floweri. Naegara floweri is a deadly disease. Sure, it kills so many people. That's why we're introducing it here. If you want to know more about Naegara floweri, go check our Naegara floweri video. We'll have Ebola. As who's next? Ebola, we also have a video about it. And if you want to learn more, come and watch it. We have HIV, who is the autoimmune system disease. And we also have, finally, rabies. Then now let's go to the ones that don't do very bad damage but still harmful. Like fungi. Fungi like dandruff can cause you to itch, but they still do damage but not going to the way to hurt you and kill you like the diseases we mentioned. We have E. coli bacteria who eat and thrive inside of you but still easy to defeat. Then we have the viruses types like flu virus and the common cold virus. Yes. And corona. You're wondering why corona in this type? Even though corona is deadly, the deadly thing about corona is the damage it leaves. So it's not dangerous. For a dangerous disease to be dangerous simply is that it's not only they have to cause a lot of damage, but to live long enough. And also in the deadly ratio, we have cancer, but it's not clarified as a disease. Now here we're going to show you the size of each disease I've explained. Now you can see most of your diseases are tiny and small. If you are trying, for example, to say, some of these diseases are so small that you cannot even see them with the naked eye or even a camera. Like for example, you need a camera on a microscope to see it up close. We also have cells you can see here. We have neutrophils, red blood cells, and macrophages here. Now we know the diseases. Now let's look inside of them. For example, we have a bacteria and its stages. Here's the first stage where it's coli, where it looks like tiny balls that grow inside of you. Then rods where they hatch, and then spirals where they multiply. Inside of them you can see plasma, ribosomes, fluorium, primer, plasma membrane, DNA, cell wall, collapse, and Philips. The Philips, I'll talk about all the parts of these. The Philips help it to sense your body. That means it clings onto you. That means when you get dirty, even though you shower, most of them are still stuck on you. We also have the plasma. The plasma helps to hold integrity in the bacteria. We have the plasmid that helps it. The plasmid scans its DNA for corruption. We also have DNA, that's the main part of every cell if you know. We also have the plasma membrane and the cyclones. The cyclones are these molecules that help the bacteria to gain its weapons. We have the flagellums that help it move and the ribosomes that help it clean its DNA. Now, your skin. Now we're going to talk about each part of your skin. We have, for example, the first part is the acid layer, the one you can see and touch. To you, it cannot burn you because you literally have acid on your skin. This one makes your skin color, that's why you have different colors. The acid normally absorbs vitamin D, but kills pathogens. Then below it we have dead cells. These ones are the cells you can scratch off but leave no damage because they're not alive. Then we have the democyte cells. These ones are cells that hold your skin's integrity. That means you can stretch it, scratch it, but they will still hold each other. Now the basophils, the base of the everything. For the skin, it's like a pattern. The basophils multiply into two. The second one moves above the sun and becomes a basophil. The basophils multiplies 5 times, then that cell goes into the second stage. That's when they produce aphrodines. Aphrodines help in also creating melatonin. After this, they go to the top where they die and then to the very top when they melt. So that's why your skin is mostly like a death wall. Cells are born and grow up to die. Now we're going into the cut, or also known as where we talk about the infection. Now for the infection, I'll use this book to explain. 10 minutes in, the bacteria enters as a non-useless threat. It enters sneakily through cuts and entering. While entering, it tries to disguise itself like a cell, hiding itself from the immune system, but still weak. Then the bacteria now decides to multiply. 10 to 14 minutes later. Now we'll have thousands of bacteria. And then finally your immune response kicks in. Macrophages and neutrophils come in and eat as much as they can. Macrophages are the fast defenses. They come and eat all those bacteria. Now the bacteria is getting eaten by the macrophages, but there's too many. So some macrophages call in for reinforcements. Neutrophils from the blood comes in and also creates inflammation. That means when you get a cut, you can feel the pain out minutes later from the incident. Let's say, for example, you accidentally cut yourself with a scissor or some sharp item. 10 to 14 minutes, you might feel a certain urge, but then the pain gets worse after 10 to 14 minutes later. That's when the defense is really kicking in. Neutrophils eat and kill themselves to make an acid barrier. Now for the first defense, it's mainly consisting of acid barrier and eaters. The eaters eat the enemy, while the acid barrier makes itself harder and harder for the bacteria to thrive and preventing it from multiplying. But still, your enemies still outnumber this fast defense. 10 to 14 minutes later. Now here the defense is really holding. The fast defense is holding long enough as it can. Then the next one, we start small. A dendritic cell from the battlefield had been scanning enough and went to the nearest lymph node. Now in this time, it's searching for every T cell born enough to fight. While they search and search, some ignore, but one assists to fight. After that, the T cell gets ready to multiply into thousands. We have soldier T cells and activator T cells. The soldiers go into the fight and help the macrophages and neutrophils still fighting the disease. While strengthening your immune response and holding it faster, The cells are feeling like to give up now, are energized again. Now we go to the activators. The activators have one job: look for the B cell. Now there's millions of B cells, so that's why there's many T cells as well. The T cells look until they find the right B cell. The B cell switches into two normal B cells and produces a slow amount of antibodies and plasma cells. With both of their advancements, we continue to the battlefield. Now the virus is gone. The bacteria or virus is neutralized and the body knows it's time to get rid. The plasma and soldier T cells die in hence for it, while the memory collectives stay. That ones are the normal helper T cells and the normal B cells. Now we're going to 8. Innate immune system. Now, what about the innate immune system, you're wondering? Well, even though the innate immune system is just your first layer, it also has credible techniques of starting. Number 1, infection. Now, this is when the infection already happens and it's still slowly growing. For example, it'll take a few days until cancer gets its full maximum. And within a few days, your body is doing nothing. That's a way to energize your enemies. And knowing what? That's bad. But for the innate immune system in the background, they're also healing and strengthening. They're strengthening their energy to fight. While fighting, they also get prepared. Now, after these days, the real infection starts. Cancer is now fighting your body in high amounts. Many macrophages and natural killer cells come, for example, like others, many natural killer cells and macrophages also come into the fight. In each infection, it starts like the infection already happening and then the innate immune system ready to respond after those few weeks or days. Now, it takes a few hours for the immune system to hold its defenses strong enough to hold each other. Now the defense is forming and it's strengthening. It's now preventing the cancer, bacteria or virus from spreading. It's now containing it. For the innate immune system's job is not only to kill the disease like normal, it's also to contain it long enough so it can weaken over time. Now, we also have phases how these innate immune cells eats. Number 1, grab. They grab the disease and hold it. 2, swallow. They swallow it and put it in a nice package. Then finally, acid. Then they excrete the waste as proteins. Now, these proteins of the bacteria can be used to improve your body. That's why in the battlefield we have cells that clean them up for nutrients. Now, inflammation. Now we go to the next part of this is inflammation. That's pain surge you get. In this inflammation, we mean like parts that insist of pain, a lot of it, like surges, sharp cuts, and pain. But these ones cause inflammation. Turning, like for example, they heat up the temperature of the battle, making it swell so it can be obvious. Yes? And also finally, they improve your immune system's attack weapons. For example, the bacteria that could infect you earlier ago was thriving in the cold temperature. Now since it's holding, the fire of inflammation is heating up the battle, killing more and more. Now this inflammation also brings a complex weapon. We call the complement system. This is a blind system completely. It cannot see, but it can still fight. Now, since cells can't do anything, you're blind basically. You cannot see the world. Cells don't have eyes or ears to see. So that means they have to use their senses. For example, they need chemical cytokines to touch each other so they can know what communication it is. For example, green equals neutrophil, red equals natural killer cells. That means that's how it will be easy. The more red it comes, that means that's a natural killer cell. The more less, that means it's close. Now, how do the cells receive? We now know how they talk. Now, how do they receive the message? We have molecules. Molecules are also proteins themselves, made out of DNA. These proteins catch the signals and now transmit them to the nucleus of the cell. Now, this can also the cell could interpret them, and now we go to the system of the complement. Remember the inflammation? The cells are communicating, helping them fight even more. We now go to the real lethal killers, the complement system. Thousands of them arrive to the wound. Thousands kill more and more. They kill and kill. This is like a blood matter that never stops. We have 21 of them. Now let me show you a process, as you can see here. Number 1, C3 and CA3 and C3 and CA3B and C3A. Those ones break apart. C3A connects to the bacteria, while the B molecule connects to C, and then the D molecule connects to B. They make a convertase, as you can see here. Then the convertase activates more. Soon, they cover the bacteria. Now for the bacteria, this is bad news because, well, now they can't move or fight back. Now after this, a chain reaction starts happening for the innate. After the infection, your macrophages come and kill, then your neutrophils come and also kill, then inflammation, then the complement system kills the bacteria, and then the infection slowly weakens. Now we're containing it and also killing it faster, but still not enough to destroy it. In the battlefield, we also have dendritic cells, neurons of your immune system. They scatter the disease area when they find it. Normally they kill and cover themselves. Then using the communication, they now tell other dendritic cells to do the same thing. Now we go to the superhighway. Remember the infection. Now we need a super strong defense to finally end the infection. The adaptive immune system. Now, for that, your dendritic cell needs to know where they are, and they need to go there fast enough. If they don't arrive in time, the bacteria will overwhelm your innate and your also very high complement system, spread immediately, infect the wound, and finally spread the rest of the body. So it's time. The bacteria are still being kept holding in one area, but not forever. Their defense is slowly weakening. So we have lymph nodes. We also have organs. We have lymph vessels, lymph nodes, thymus, and spleen. All these organs, like the lymph for example, transports your dendritic cell from one organ to another. The spleen transports its nutrients to the battlefield. The thymus, where the university for each cell, and finally, your lymph nodes that contain, each of them contains a sac of T cells. Now, we go to the super weapon's arrival. Now the dendritic cell is activating your weapons slowly. Now the fast grouping comes and kills the bacteria using their weapons, heating up the area more and making the defense of the innate immune system, healing the innate immune system while strengthening it. Now the battle is starting to get a win for the immune system. Now the laboratory. Now we're going to talk about our super weapons. Helper T cells, killer T cells, cytokine T cells. We also have regulatory T cells, macrophage. We also have mitochondria, and finally B cells and plasma cells. These cells, and also memory T cells and memory B cells, are cells that help the immune system. For each of them, they have to learn a specific weapon. And the weapon can be anything. It can be, for example, it can be a weapon that can kill malaria. It can be a weapon to kill this bacteria. It can be a weapon for every kind. But this weapon has to match with the receptors on the dendritic cell. Now we are going to talk about those specific receptors on these cells. Now for this one, we're going to talk about the way and how these T cells fight. Now using the fighting power, they fight using those receptors. Imagine this, an army of cooks, 5,000 of them in total. Now imagine Gordon Ramsay says, cook me the most delicious food under 10 minutes. That's a short timer for these cooks. But using their time, they make very good foods. How is that possible? For example, the timer is the time they need for the T cells to activate, and the timer is how they make their weapons very fast. The food is the weapon. So now that means we have millions of combinations. That means RF merge BF makes a viral killer receptor, while DF and CF make a bacterial one. Until then, while still making, we have the thymus killing T cells in the thousands. Only 2% remain, and that's why you have 2 million T cells in your body. Now after this killing session, the T cells are ready, the dendritic cell finds the right one and activates. It multiplies and multiplies into thousands. Now we're going to talk about your thymus. Your thymus is a mother university. Imagine a normal university, this time with murder. If you fail your exams or any work, you die. That's why you have to get essays in everything, so you can live. Except the majority of you will die at any point. See, you have to correct your mistakes, and that's how it's like in the immune system. I'm at a university where T cells are constantly being trained and killed. And it takes a few days for the T cell to get ready. Now, here's the questions that you might find. Function receptors? Yes. Good at communication with other immune cells? Yes. Recognizing self? No. The C cells that say no survive, while we also have death points, as you can see. No is death here, no is death here, yes is death. Now after this, your thymus lies here, on the chest. Now the T cells are fully trained, and we now go to the antigens. Now here we can see a basic antigen receptor right over here. The basic of this is how it's formed, in which you may see we also have the T cell tree. This one you can see every T cell. We have pre-T cell, virgin T cell or regulatory T cell, helper T cell, killer T cells, and their memory versions. Tissue-resistant memory T cell, effector memory T cell, and central memory T cell. Now these ones are the T cells that help you. In this tree, you can see signs like thymus training, activation MHC2, activation MHC1, interfection over. Now with this, the immune system is activated. The dendritic cell finds the right T cell, activates the right cell, and then the infection starts by the infectors. Now we're going to the final end of the bacterial disease. The final end of this is the B cell. Now the B cells also have their own, but it's more complex and simpler. Bone marrow training, virgin B cell, activate through antigen B cell, activation through T cell, and now infection over memory B cell, infection over long-lived plasma cell. So that means we have plasma cells and B cells. After the fight, we have them. Now we're going to the last part of this disease. Here you can see a bacteria antigen to the B cell. The B cell multiplies and has indicates that the T cell is now activated, finds the right B cell and makes a plasma cell. The plasma cell produces a lot of antibodies, weapons against it. Now we're going to talk about how is this activation possible. See, the T cell has a different receptor and the B cell has a receptor to connect with it. Now it's kind of like a game of gambling. You won't know what you get until you merge them. The right ones fit, the wrong ones fail. Simple. But it's random. So it could be random if 1,000 B cells in your blood have different antigens. That's why the T cell chooses wisely, tapping every B cell in its path. When it finds the right ones, it activates. Now, we go back to the battleground. The disease is holding while the disease is awakening. The bacteria at its last strike and the antibodies come in huge amounts, stinging and clicking onto them. After clicking onto them, they hold enough, and then stick the bacteria. Now your defenseless enemies are slowly but surely cleaned up. Here's the types of antibodies for each disease. You can research them on your own or continue watching. Now, after your antibodies have neutralized the weapon, we now go to the end of the first one. Now we're going to talk about accidents. First, hostile takeover. This is when a disease gets dangerously leveled. We're going to your gut now. We left the lymph nodes to your gut for one reason. Here's a portrait of your gut. You can see all the cells I've explained and how is it going. In your gut, we have thousands of bacteria and viruses in your body. We have macrophages, T cells and B cells, helper T cells and B cells. The B cells help by attacking the bacteria while the helper T cells slow down the attack. Why? Because this is the problem with your gut. While also it's full of bacteria and the most dirtiest place in the body, it has to be also cautious with the immune system. If, for example, if these helper T cells weren't there, your gut will suffer an infection forever. Like an infection that will happen multiple times. That's why your T cells and B cells are there, to slow down your innate immune system so it cannot kill you. We also have M cells and goblet cells in making mucus. The M cells activate it and personal response to the dendritic cells, while the goblet cells produce a wall of mucus, protecting you, separating your gut from the diseases in your gut. That's how your gut functions, basically. It also not absorbs food, but also keeps the separation. Food enters while bacteria stay out. Now, we're going to talk about how your immune system deals with the gut. Now, the gut is the most complex part of your immune system for one reason. It has many bacteria, and your immune system has to fight all those bacteria. And your immune system those bacteria can also communicate to your immune system. For example, the bacteria has a molecule that can change T cells completely. For example, a helper T cell is normal, but thanks to a cytokine in the bacteria and the gut cells, it can transform into a regulatory T cell. Regulatory T cells have a role in this function by shutting down or permanently slowing down your immune response. But we are going to talk about them later. Now we're moving to more dangerous circumstances that even your body will know. The grave of the death. Now, this one we're talking about viruses. From ancient, probably scientists have like other explanations how these viruses came to be. But the simpler term in long time ago, some cells divided but weren't successful enough. And these unsuccessful cells died. Even though their dead bodies are husks, they need to infect other living cells to make copies. Well, that's not even the truth, but we don't know. Scientists are making hypotheses right now where viruses came from. But yeah, we're not sure. But for viruses, viruses are pieces of dead matter that infects living matter. That makes no sense. How could something dead and tiny infect something 10 times larger than it and it's alive? Now, we go to the point where it makes no sense. How do viruses even reproduce in the first place? Viruses aren't alive and they cannot do anything. They can't eat, they can't breathe, but cells can. So the way for them to reproduce is that they have to infect a living cell, reproduce inside of it, and get out. But how does the cell make more viruses? They can't split inside of the cell, or else that's game over. The cell just makes a copy. Like imagine this, a factory making proteins, and the virus is a hijacker or a hacker hacking this laboratory. Now the machine is told now to make more of the hackers, to hack more machines. Now that's how this happens. The machines are cells and the virus is the hacker, hacking living cells to make its same copies. Now we have a general point here. First, the virus hacker enters the wall of the cell or the membrane. It quietly enters as a protein from the gut or any part of your body. Now the genes have been transmitted to the cell, hacking it. Now when the cell is hacked with the new DNA, it now makes an order to produce a lot of viruses. It makes so much and there's apoptosis. Then those cells are hacked and then the disease spreads. Now, we also need to talk about parts of your respiratory system and your immune systems. We have the part in your nose where it's hairy. Your nose has a hairy part preventing viruses and bacteria. That's why you have mucus in that hair. Yeah, your esophagus, this that leads to the lungs or bronchial tube or air pipe, has mucus layer. And now we have epithelial cells and alveoli and macrophages in your lungs. And we're going to talk about the immune system in your lungs mainly, so just keep in touch. How does viruses spread to one person from another? Now, the main part of a disease is to spread it. After infecting your body, the disease has to leave and find a new host to infect. Like a chain reaction, once you get infected, you have to infect another person. So the person coughs it out. In these saliva bubbles, we have viruses. Any virus like influenza or corona or any just live in that bubble. The bubble lands on somebody's face, nose or mouth and infects. The cycle continues. Now here we're going to show you how this appropriate system works. Here first we have the hacker. Here's the security system, for example. The security system in this case is the protein here. Now, viruses have a receptor like a key card to hack these security systems. Well, the security system prevents bacteria from entering, but viruses have a cheat code. They can hack the security system and enter. Now the guards receive them in. Unknowingly, like imagine this. Your guardian receives a stranger inside of your house who you have no idea in. Now the bacteria is surrounded and kept inside safely. Your antiviral defenses are out here, outside this smaller cell you're being inside. Now we go to how the infection works. The infection takes slowly but surely, and then a few days happen. The cells now realize they're infected after all these days. Yes, that's pretty so for a cell, but because the virus is sneaky and hacking their systems, it's very hard to determine which cell is not hacked and which one it isn't. So the infected neighbor cells who know which cell is infected the fast make interference or something like a letter to the others. The other cells receive the letter and then shut down the protein systems or shutting down the factory so the virus could not spread. Imagine like this. We have our hacker here. It has hacked a group of cells, a group of factories. Now those other factories receive a message that they're going to be next. So they shut down, isolating. The interference also activates your police cars. For the police cars they're basically your immune cells. Our police car, the first receiver police car is your dendritic cell, scanning in the disease. The police knocks at every door and tries to find which place is hacked. When it finds the place it hacked, now the interference have made the cells to be easy to be found. Now we need to know which cell is hacked from the inside. Now, before your polices could attack and destroy the enemy, before your immune system can activate a permanent weapon, they need to know what's going on. In bacteria, it will be very obvious because they don't enter cells and hide in them. In this case, they're inside. So that means the immune system are blind and cannot see them. But the interference do more. They make the cells make MHC class 1s or 2s. These ones make the cells like a window. Imagine a house open its windows to show what's inside. Now the police checks inside and sees the hacked ones. Now your defense starts to form. Now after the windows are opened, the windows show a glimpse inside. Imagine these windows show a place where the hacker has hacked. Now the cells are showing the windows inside, showing which ones have been infected. Now the cell now knows. Now it causes. We now need to list the examples here. The examples of cells with MHC class 1 molecules are basophils, and also normal cells, and also your tissue cells. These cells have these MHC class 1s. MHC class 1 is a window seeing what is inside these cells. For example, a basophil. It's showing these insides to a T cell so it can activate. MHC class 2 are from dendritic cells, macrophages, or B cells. Now for MHC class 1s, that means that I'm trying to send a signal to the cells, like to your adaptive cells. For MHC class 2, it's actually just telling them to help the battle. Now, we have two different types of soldiers, you already know. We have our T cells who analyze the situation. We have our police cells who kill the situation. That's why they are both different in each way. Now, we can also see how they represent. The T cell reads information, while the killer T cell needs directions. Now, the process begins. Your police T cells come in. The killer T cells search every cell using the MHC class 1 molecules, scanning and scanning again and again, until it finds every cell. Now, your police kills them. To recycle, then your macrophages eat them. A simple process. The police finds, order it to kill itself, then it dies. Now your heavy defenses come in. Now fast police, then tanks. And our tanks are natural killer cells. For example, how could the hacker hide its identity? Number one, it could order all of its factories to close its windows. That means it's basically invisible. Now our police cells are blind and cannot see the enemy. Now, without seeing the enemy, they cannot see it inside or out. So they think those cells that are invisible cannot be seen. Our tanks look for the unexpected. Our tanks, also known as natural killer cells, look for cells without that MHC or that window. Now, when the tank finds that place that has no window, the window is supposed to mean something like, for example, what are you hiding? The natural killer cells are looking for what the cell is hiding. A cell without MHC, that means it's hiding something. Something that's infected. So your natural killer cells find it and kill it. Now your defense is forming and forms a strong defense. Meanwhile, your helper T cells go and find B cells. The B cells activate and release antibodies. Then the infection slows down and dies off. Now, for the virus one is much complicated. Number 1, you search the enemy. Number 2, you kill the enemy. Number 3, look for the unexpected. 4, make a strong defense. And 5, neutralize. Now we're going to talk about the ways of shutting down your immune system for the enemies. Now we also have a deactivator cell. This cell is the one that deactivates your weapons. Let's say, for example, our polices and weapons are now tired from fighting. The regulatory T cell is the safety guidance system. That means it controls how much weapons is released. But also this cell is found in your brains and also your heart. Those are the 2 places where these cells are found. When they found out the infection is over, they now send calming signals to your weapons to shut down completely. Now we are going to talk about the last thing from these 2 diseases is memory. Memory is to remember that something. For example, a T cell could remember that thing. Let's say we have writers. Writers used to be a person who fights. Now they write and remember. When that same infection happens, they're ready to fight in heavy numbers. But at the cost. For example, here, after every infection, some cell dies and some remember. The cells that don't remember are useless after the battle and have to be killed. But the memory cells stay in your body patrolling for that same disease again. If a second strike happens, they'll attack immediately. Now we're going to talk about your blood, the ocean of your body. We have, for example, one blood cell. A drop of blood, 250 million red blood cells, 400,000 immune cells, 15 million platelets, 13 trillion antibodies. Here's a perspective of our one blood test. It can see everything that is inside one drop of it. Now, the human body has a lot of blood, so multiply this one drop by 1 liter by 1,000. 1 liter of blood will already have 1 million helper T cells and a few other cells we can talk about later. Now we go to vaccines. How do vaccines work? The reason why I'm talking about vaccines are because vaccines are very helpful in one way and another. For the vaccine, we inject it for one reason or some other. What are vaccines and how do they help? How do vaccines even help in the first place? For vaccines, imagine this. Somebody ejects the same enemy, but this time weaker or dead. Then your cells do this normal infection thing, attack. The weaker disease spreads and doesn't get strong, but the infection is clearly wiped out. Then this time, the body spares more cells because more cells will remember that disease. Now we go to rebellion and civil war. This is when we have weird instances of cells rebelling against your body. HIV. HIV is that hacker that is more complex than the other. HIV is targeting not these factories, but your cells. Your police cells that help you. It starts off slowly. The hacker is hiding from your weapons. The main weapons that can kill the virus are now targeted. The virus infects them and hacks them. These hacked cells now produce more of that virus. Now more of that hackiness spreads around the adaptive immune system. Now when they spread too much, the body has to find out how to get rid of these hacked cells. So that means they send in more and more weapons that end up dying at the end. The hacked cells die and your body cannot do anything. The hacker still hacks more, but your body then finally supports a giant weaponry that crushes the disease at the end. Like HIV, it might be strong at the beginning, but at the end, and eventually to be destroyed, even without medicine. The immune system aggressive to allergies. Allergies are foods that might look dangerous to your body. For example, eggs, pollen, for you they won't look dangerous, but for your body they look harmful or even poisonous to them. So your immune system starts attacking these painless objects. First, our B cells activate from these islands, make attack to our mast cells, or also known as our bomber people. These people throw out grenades in the body. Now after being activated, the grenades spread and causes inflammation. Normally inflammation is a good thing, but it's not in this case. Now how does your body miss the parasites? Parasites are different completely. They are a different way than normal than you can expect. They are that disease that finds a way to enter and leave your body. We have like a few parasites or NTDs. Those are a group of parasites that are dangerous. But what are these parasites mainly? Parasites are things that enter your body, take over your body, and live inside of you. So you have an organism inside of an organism. Now this time, unlike the mitochondria, this organism hurts you in many ways. Parasitic worms take your nutrients, making you weaker and weaker every day. Bilharzia drinks blood. Those ones can be deadly because blood is the most important part of your body. So how does your immune system miss them? The parasite is sneaky and acts like an organ. For example, when a parasite bites you, it doesn't mean it's taking control of you or something. It acts like an organ. It bites at a specific way and makes molecules around that bite place. The molecules improve the blood vessels growth into the mouth of the parasite. For example, if a parasitic worm bites you, the chemicals will force the blood vessel to enter inside the parasite. So getting rid of a parasite, it means you're cutting off a blood vessel off of you. Sure, the parasite is with the blood vessel. That's how it drinks. It doesn't harm you. It makes a blood vessel grow inside of it. That means it's drinking your blood from inside of you. That means it's not like a vampire. It's more like the blood is force-fed into the parasite. Now, this is like a way to change your blood. Now you have a very new blood vessel attached to the parasite. That's why scientists and the immune system has to be cautious when killing a parasite. Because if you kill the parasite, you kill the blood vessel completely. Now that's how your immune system has to find out. We also have parasitic weapons that cut the blood vessel from it, but they only separate the blood vessel from the parasite. Now when the parasite is holding it, they fight back. The immune system fights back in massive force, makes chemicals that act like acid, burn the parasite, melt it, and then turn it into a waste product. Now the parasite is excreted. But even these weapons parasites can evolve with. A parasite is kind of like that person who's always adapted to anything. Whatever the police throws at this enemy, it always adapts in different ways. Is in the other way. Autoimmune diseases. Autoimmune disease is when your immune system gets confused from different cells to another. This means they get confused from this and that, and they attack the wrong thing. For example, an autoimmune disease cell who is not properly trained from the thymus could attack your body and cause an autoimmune disease. And then, you start having an infection that's about you versus your own self. Imagine this, you're fighting yourself right now. Imagine how hard it would be to survive from yourself. That's why some diseases make this happen. Some diseases disguise as your cells to hide. And now since in cells some diseases look like your cells, the T cells and B cells from this fight get confused. Like, that means some cells in the battle will start attacking you even after. And that will cause an unlikelihood of forever pain. Because of memory, T cells can remember that, and they produce antibodies that kill you. And still, that's how autoimmune diseases work. But don't worry, these T cells get killed immediately afterwards. So, they are lethal, yes, but they're going to kill you. Now, we'll have to learn about hyperptosis. This one means creating your own medicine and ingest it. Now, your own medicine might not look perfect like the scientists, but still, it's highly unadvisable to create anything by yourself. Even schools don't make medicine for a reason. Scientists are highly professional people who make ointments, treatments whenever necessary, with the right chemicals and right things. If you don't make it the right way, it could end sideways and you'll get sicker and sicker. Like, imagine taking a pill and you get sick. Now, to strengthen your defenses. Now, to strengthen your defenses is easy as lemon squeezy, but most people will find it disgusting. For example, liver meat. Liver is the most organ that associates with the immune system. With a very high amount of energy inside of it, it helps you grow strong, fight diseases faster, and make you better. But most people describe it as a bitter taste or something worse. But still, you have to be healthy first. You have to eat healthily. Liver meat, replace chicken with liver. Replace junk food with healthy food. With those things, you can strengthen your body. Now, we're going to learn about stressing the immune system. Stressing the immune system is simple but also hard. For example, eczema, stresses your immune system by faking a disease. And some diseases like Ebola fight hard while infecting the immune system, stressing it even more. While stressing the disease will get weaker and weaker, and the immune system will also get weak. So it's a life or death scenario here. Like, now your immune system is weak, and also you're weak, and your enemy is weak. Whoever does the final blow wins, and whoever doesn't dies. So that's why it's very dangerous for Ebola or Naegara floweri, because they reach this point and always survive. So the thing is your immune system cannot fight an enemy it cannot deal with. Now we're going to cells who are too corrupt. Corrupted cells. Imagine this. A factory gets corrupt, not by the hack or anything, it just gets corrupt. Now the corruptness changes it completely. Changes and changes. The factory multiplies into billions and thousands. Now this corruption makes a cell called cancer, the corrupted cell. Now your immune system has weapons, same viral weapons, same effect here. they attack the same way. But instead, unlike viruses that cannot fight back, we have phases of this. The first phase is when your polices and gunners finally arrive, shooting at massive amounts, making sure the cancer can suffer in heat stroke or anything possible. But the weapons do not damage that wall. More and more cancer cells make a wall, strengthening it. The second phase is when your immune system brings in heavy amounts of cells fighting. And also the cancer cell is fighting back by recoding those immune cells as to be regulatory T cells, shutting down those cells. And then finally, the cancer cell spreads all over the body, killing the person. Now we go to coronavirus. The last part. Coronavirus is way different than you think. Sure, it infects your lungs, but the way it fights is way harder. The cells that fight in it are trying to kill this virus, but the virus spreads and spreads. By the time when your immune system arrives, it's already done the damage. Slowly but surely, your immune system fights the disease and wins at the end. But already too much damage is already formed. That's when the person has a true fate of dying. But luckily, us humans made COVID-19 vaccines. So that means, how does this vaccine work? Like all vaccines, it has to start at the beginning of the infection. Like at least one day early or a few hours. As a few hours as soon as you get the disease, rush to hospital, get a vaccine injection and wait. The injection will kill the virus and make some of it, not making... The vaccine is not helping you live, it's making you survive the disease. And now we're going to talk about functions and parts of the immune system. The last part. Here, I'm showing you a diagram and I'm going to explain it. Now, in this diagram, we're going to start in the innate immune system. First, the metamorphosis. Monocytes become macrophages, neutrophils. Now, we're done with that. Now we go to communication. Neutrophils communicate with macrophages and dendritic cells. Macrophages communicate with natural killer cells, communicate with neutrophils. They also communicate with helper T cells and also communicate with the dendritic cell. Natural killer cells kill virus, infected cells and cancer, while your neutrophils and your macrophages, complement system, and dendritic cells kill viruses and bacteria. We have parasite killing cells like eosinophils, basophils, and mast cells that kill the parasite worms in your body. Now we're also going to talk about the adaptive immune system. We'll have the way of the killer T cell's life. Virgin killer T cell gets activated, turns to killer C cell that kills its viruses. After battle, it becomes a memory killer T cell. Now we have virgin helper T cell that becomes helper T cell and then becomes memory T cell. For B cells, they have 4 stages in their lives. We have B cell, virgin B cell to B cell to plasma cell to long-living plasma cells, or B cells to memory B cells. Killer T cells communicate to helper T cells. Dendritic cells communicate to virgin helper T cells, and all the B cells produce antibodies that also kill bacteria and viruses, and also parasitic worms. In this sense, we now also learn that since we come to the end of our video about the immune book, and if you enjoyed this video, please like and subscribe.